So last time we learned about the integration by parts, okay? And I let you to use a new kind of patterning the integration by parts by taking this as like a table, okay, table, and then you can see that we can cross multiply, and then we can arrange this integration by parts. Okay? So this is actually the same thing, but what's interesting about this method is whenever you have the last part is still integration, because we are not sure how many times we need to integrate. So you can do it as many as you can, but usually we will stop at when the d, this part here, the left one, when it's getting 0, then we will get the final answer. Okay? So usually that is the way. But not every case will end in 0. So sometimes you just need to stop, and then maybe we need to rewrite or maybe rearrange the integration in another method. Okay. So let me show you. But perhaps let me just take a look. Similar questions like this x sine x. But let me write taking the x as x squared and sine as sine 3x. If you are taking this components of integral, taking this as u, this is dv, we can start like rearranging as the u phi minus phi du like this. But you will notice that at the integration of phi du, we are going to take integration by parts again, right? So instead of doing this, let's just try our d I, and then put all the information, so x squared, and then the other part will be the sine 3x, and then derive and integrate become negative cosine 3x over 3, right? And then still we have 2x, derive become a constant 2, and cosine integrate becomes sine 3x, and now divide by 3 by 3 is 9, right? And then derive again, this 2 becomes 0, and this part becomes negative, so it's positive cosine 3x over 9 multiplied with 3, 27. And we need to add plus, minus, because the formulation is, let me write here just to make you remember the concept, the principle, that we have positive and negative, right? So we have positive, negative, positive, negative. So taking cross multiplying all this, we get the final result is negative x squared cosine 3x plus 2x sine 3x, and then plus 2 cosine 3x over 27. And don't forget to plus a constant, okay? Because this is indefinite integral, so we need to make sure that we have a constant at the end. My suggestion, this c, you can add like at the very last part of your process. Sometimes when we add at the middle, you will get confused on how the constant will be. But let me just add in the constant at the very end of the process. You can try using the same method, and I believe the answer will be the same. Okay? Will be the same. Okay? I think this will be very helpful if you can identify from this component, the integral, we can identify which part that when we derive, maybe it will reach 0. So we can decide that will be our u, and the other part will be our dv. And derive, integrate. So I'm trying to finish by today at least 2 or 3 sections in chapter 7, which is the trigonometric integral, trigonometric substitutions, what else do we have? Yeah, probably the partial fractions method, a method to simplify the fraction integral. Dx, we can take this. Okay, this is just to simplify, right? Because dx can be in x squared or can be in sine, right? But that will be the same thing. Right? Same thing. So if we take this, it will make sense because it's integral. You can add also here dx here. Okay, now let's see another example. Okay. Now is e with power of x and then sine x dx. Okay. Okay, let me give you time to check this one. So now we have an exponent e with power of x multiplied with sine x dx. Okay, let me give you a couple minutes to try. And using the integration by parts. The final exam, probably my estimate time is around end of December. If we cannot make it, maybe first week of January after New Year. So you will celebrate New Year with the preparation of final exam. but I want to make it like in the end of the year. So after that we will have well, maybe if we still have makeup exam. But if not, then finish all the semester at the end of December. Okay, confused with last one here? Yeah, because this is interesting, because if we think e and sine, if we derive or take integrations, both of these components, they are not reaching any zeros. So they will, e is still e if you derive or if we integrate. Sine will be sine, cosine, right? So what should we do? So we can still do this thing, okay? But let me just stop at some points, okay? And you will also know how to make that happen. So let's try this d I, and let's just say that we are going to take e to the x and sine x here. So derive, integrate, okay, and then derive again, and then integrate, and you will see that it's becoming another sign as it is in the original equation. So I decide to stop here. Okay. And now we need to cross multiply here and also multiply this one, but we need to take the integral. So let me write on the right side here that this will be negative e with power of x cosine x, okay, plus e with power of x sine x minus integrations e to the x sine x dx. Okay. So if you have the cross multiply like diagonal line here, that will be this one. And when you have this horizontal multiplications, you still need to write the integral. Okay. And now, this is the beautiful thing in this type of cases. You will see this, and you will see this, the same integration. So we can move on this part, move to here, and we can plus becomes 2. Okay? And then we can divide all by 2, and we get the answer. Okay? So let's do that. So we get 2 and then negative e and don't forget plus c. Okay, so my suggestion add at the very end. So we can also solve this integration by parts just by arranging and maybe somehow finding the same component as the original integral. Okay. Now the problem with this kind of integration is if you're not realizing that this part is the same as the original one, what you will do is you are going to integrate this part. Okay? Again, you will have some equation, and the result will be really long, right? Really long, and we will not like ending really nicely. But when you realize that this part is the same as the original equation, we can just solve by algebra. We just move into that side, and we can solve all the integrations. Yeah, sometimes when you deal with the questions and you're not see the big picture, the whole equation, what you are doing is you are going to integrate this, and again you will have a really long integral. Okay, now let me give you a couple more example how to use this method, and this method is quite nice, really helpful, especially if you can identify which part that you need to derive, which part that you need to integrate. Okay? That's the important point. Okay, let's try another example.
Let's try integrations of tangent inverse x.
Tangent inverse. Okay, let me give you a couple minutes to try.
It seems really nice, but then maybe not so nice. Anyone solve it? Yeah, yeah. Yes, yes. You can check the website, Wolfram also. It's for all mathematics complications. You can put integral really help. Yeah, yeah, yeah. You can check this also, and you can find the answer there. So if you want to check using your browser, there is a website called wolframalpha.com. Okay. This website is a computer intelligence machine learning that can compute all mathematics process. Not only mathematics, but all questions like social science. I think I already gave you this at the beginning of the courses, but I think not all of you try to find it. But you can try to find it now. You can tap smartphone, go here, and you can take the integrations. I think they provide you some formulation for equation. You can take integral and input the tangent inverse. There are some special comments in the functions in the website. And you can try this for all your homeworks, even quiz. You can try to check your answer. It doesn't give you like all the process unless you pay for that website, like Premium, the Pro. But it will give you the final answer. Sometimes the final answer may be a little bit different because in integral, we can have a different interpretations because of the constant, the different in the constant. So we can have many variations of the result. You can check using this, and this is really helpful. And sometimes it's also helped me to check the questions and maybe to decide which questions for the exam. It's already correct. Yeah, correct way. Yeah, you did it really good. Okay, now if we back to the question, the tangent inverse. This is just having the tangent inverse and the x, right? We know for sure that the tangent inverse, we know the derivatives, right? What's the derivative of tangent inverse? 1?
1 over
Yeah,
x squared.
1 plus x squared, right? So let's say we are going to take that as our d, and this dx is our integral. So we derive this and we integrate.
So tangent inverse becomes 1 over 1 plus x squared, and the x becomes just x. And then let me just stop here. And the equations become x tangent inverse x, and then minus x over 1 plus x squared dx. What's this actually? We can solve by substitutions. Right? So take substitutions. Okay, sometimes the integration by parts can solve in combination with another method as well. Okay. So we have this will be 1 over u du, right? So 1 over u du is ln u, right? So we can write this as x tangent inverse x minus, let me take this a little bit down here, minus, it's 1 over 2x, so this will be having, I forgot to half here, half. So 1 over 2 ln, u is 1 plus x squared, but 1 plus x squared is already positive, so we can write just with the bracket plus constant. Okay. Deciding or identify the components that need to be derived or integral is important. Sometimes maybe we are going to have like really long time because maybe we are not nicely calculate the equations, and maybe we need to have some trial and errors. But as long as you try to familiarize the with the question, with the practice, I think you will know, and you can identify that directly from when you read the question. Okay, now the next part, I will give you more couple questions again, still in the trigonometric, because this will be going to overview the trigonometric integral and derivatives. So we know that if we have integrations of secant squared x dx, this will be equal to the tangent, right? Okay, the tangent, right? Because the derivative of tangent is secant squared. So we can write this as tangent x plus constant, all right? Now, if we change our questions just to becoming only secant x dx, Now this is really challenging. Really simple, but it's really not difficult, but there are some tricks to solve it. Okay. So one way to solve the secant is try to multiply the secant with some, it's like rationalizing the limit, if you remember. We multiply with some fractions. Okay. But the idea is when we multiply the secant, we want to have a good structure that we can substitute easily, and we can integrate with substitution method. So we need to multiply with something here that when we try to integrate with substitution method, it will nicely canceling the form. So the idea is to have, if you remember the secant, if we let this to be derived, this will be secant x, tangent x, right? Okay. And then if you have the tangent, if we derive this will get you the secant squared. Nicely done, right? So perhaps if we multiply secant with something that resulting in this 2, and then we substitute the secant and taking this as u, and du will be the secant x tangent x. So probably if we take the secant here and plus with something, so maybe if we take this as secant x plus tangent x, if we multiply, we will have secant squared x plus secant x tangent x. Okay. So perhaps if we take this secant x plus tangent x, this is as u, then we could take this and make the u as secant x tangent x plus secant squared x, which is perfectly the same as when we multiply these two. Okay, so we can cancel these two forms. So the idea is taking the secant x and multiply the secant x with secant x plus tangent x over secant x plus tangent x. Okay. So this will be secant squared x plus secant x tangent x, and this will be secant x plus tangent x dx. Okay, next part is taking u substitutions as secant x plus tangent x, and by doing so we are going to have secant x tangent x plus secant squared x dx. So we could cancel the whole part here. So we are having a nicely 1 over u So integration 1 over u, and this becomes ln of u, which is ln of secant x plus tangent x. Okay.
So this will be, maybe I will write, going to be here. So this will be integrations 1 over u du, or this is ln u, or ln secant x plus tangent x. And don't forget plus a constant. Okay, the next part, we know the secant x, we know the secant squared x. How about we get the integrations of secant q? Okay, let me give you some times to try.
Also take secant with the power of 4, power of 5, and you will see that at the end, you will see some pattern for the secant. Well, the secant x is the exceptions for the process, but when you increase the power, you will see more and more like a pattern. But if the power is given, I think it's easy to follow, because secant squared we can integrate easily, so we can use substitutions if the power is given. But if the power is odd, what we can do from here? We know for sure we have the result for the secant x, and we know the secant squared. So let's say we take secant multiplied by secant squared, and maybe from that point of view, you can see more clearly. Because in terms of difficulty, the first part of our course is mostly about the derivative. The second part is about integral, which is the reverse or the anti-derivative, which is, I would say, in general, it is way more difficult than the first half of the course. So, yeah, the subject will become more difficult because of the integration. And the next semester, still we deal with the same thing, derivative integrations, but the difference is, this semester we deal only with one variable, y equal function of x. The next semester we deal with the more than one variable. So y equal f x1 or f x1 is they're way more complex than that. So the difficulty will also like hiking up, increasing. And don't forget all the methods in this semester because we need all the methods in next semester. And maybe we don't have much time to review all the methods in next semester. So I hope you can take care of your notes whenever you need that, at least for next semester, at least. If you take another course related to mathematics, like advanced, like engineering of math, for sure the calculus will also take part. So please take care of your notes. I think most of you will take the engineering of math. I use the second cube is you can use the integration by parts. You can see the second cube as secant x multiplied with secant squared x. Right?
Okay, so to begin with, this secant cube, we can separate becomes secant x and secant squared x dx, right? Okay. And
we can derive easily secant x becomes secant x and x. We can integrate easily the secant squared becomes tangent. So let's try to arrange that, and then maybe we can arrange
in our equations. So we can arrange the I. So this will be secant x, secant squared x. This will be secant x, tangent x, and this will be tangent. And this will be secant x, tangent x, and then minus integrations secant x, tangent squared x, right? And we need to
solve now the secant x tangent squared x. Can we solve this? Or how to solve this? Can you try? Yeah. I mean, let me give you times to check this integral. Okay. Remember, to solve integrations, at least we have the substitutions, we have the integration by parts, and also we can rewrite the form, maybe taking the algebra or the trigonometric identity. So perhaps with the identity we can solve. So maybe what's the relations between secant and the tangent?
So if we look at the relations, what my suggestions are going to be is always take your identity from the very basic. Let me write. Since sine squared plus cosine squared, this is equal 1, right? Okay. So my way of doing this is, if you are sometimes forget how to do the identity, try to divide all by cosine squared. So this will be tangent. Okay. And now we can exchange the tangent squared with secant squared x minus 1. Okay. Now let's try to substitute this part. Okay. So substitute this tangent squared. Okay. Now you will see that this will be secant squared minus 1. If we substitute here. And if we multiply with this, we will get secant cube and secant x. Secant cube is our question, so we can move that to the left. Secant x, we already finished off at the previous questions, right? So we can write that the secant cube dx is secant x tangent x minus integration secant cube x dx and plus, this is after multiplications. Okay, so we are multiplying this with the secant squared x minus 1 like that. And then we solve algebraically. So this is 2 and then the last part is the secant x. Secant x, this one. So plus ln secant x plus tangent x. And then the result will be half of secant x tangent x plus constant.
So you can think in another possibility. We have an odd power. So if this is cube, maybe you can imagine what we will have if we have secant 5. So we can separate secant squared and secant cube and do the same thing, but I think it will be very long. It will be very long, but it's still possible. So it's still possible.
Okay, we will have a break and we can continue after the break. Okay, so we will begin the next sections, which is we call it trigonometric integral. So the idea is we are going to use basic trigonometric identity to rewrite the equation and solve integration by use substitutions. Okay, so there will be several patterns that I will just take times to give you examples how to solve each question. So the first case, so case number 1, if we have a sine with power of m x and cosine power of n x. So let's just try using like direct example. So solve the integration sine with power of 5 and cosine squared x dx. Okay, now to solve this sine with power of 5 and then cosine squared, the first thing is we need to remember the basic identity is sine squared plus cosine squared is equal 1, right? If we plus this. So now the idea is we look on the equations and we see that we have sine with power of 5, okay? So
The basic identity is sine squared plus cosine squared, right? It's having squared, squared. But now we have, this is even, this is odd. Okay? So the idea is, maybe this sine with power of 5, we can split. It becomes sine with power of 4 and sine. Okay? And sine with power of 4, we can think as sine squared, squared. Okay?
So let's try to see. Okay, let's try to see that form. So this will be sine squared x and then squared and then sine x and then cosine squared x dx. Okay, and then what next? The next is this part inside this squared here, the sine squared. We can rewrite this as 1 minus cosine squared x. Okay? So let's try to change that. So 1 minus cosine squared x and then squared. And then we have cosine squared x and then sine x.
And a way to finish off these integrations by taking substitutions. So we are going to force our substitutions to cancel all the things that I think if we take this, like this having squared here, and we have like sine x over here, this is cosine, cosine. I think if we take the cosine as our substitutions, we can cancel the sine. So this will be u, this will be u, squared, squared, squared. And we can solve the equation.
So taking the substitutions from this cosine x, okay, we can take that. Now the equations become, because it's negative, so negative in the front, let me write. And this will be 1 minus u squared, squared, and then u squared du. Okay. I think we can solve this, right? So we can take this. And then this will be negative, multiply. Okay. And then finally, we will have minus 1 over 3 u cubed plus it's over 5, 2 over 5, and then minus u over power of 7 over 7, and we can substitute back to the original equations. So cosine cube x and don't forget plus a constant at the end. Okay, that is the first case, is with sine and cosine. And some notes for the integral, especially when you integrate, let's say, integrations of, let's say, sine squared x dx. Okay. My suggestions, and because you will see this very often, especially next semester, the sine squared x dx, what I'm suggesting is we are going to take this into, so if you remember that we have this double angle formula for this cosine, right? And we can rewrite this, becomes two different forms. The first form is we have the 2 cosine squared x minus 1, and the other one is 1 minus 2 sine squared x. So the sine squared x is half multiplied with 1 minus cosine 2x. Okay? And if you write using this form for the integral, I think it's really easy to compute, right? Because the cosine 2x we can integrate directly. But when we have this, do not try to directly integrate this, right? In the derivative. So always change this squared into double formula. Because you will see a lot this kind of integrations, especially next semester. And another double angle that may be useful for the sine and cosine is the, if you have sine 2x, we can write as 2 sine x cosine x. So whenever we may be getting integral like sine x cosine x dx, so perhaps we can change this into the half of sine 2x. Okay, and then this will be easily to compute, right? Okay, this is case 1, is sine and cosine with some power, okay, above the sine and cosine. The case number 2 is the tangent and secant with some power. And because secant and tangent, we know from the previous sections that we can have the identity for those of two. We can have secant squared equal 1 plus tangent squared, right? Okay. So let me write in the new page, but I think if you want to take notes. Okay, you can take notes first. Okay, so case 2 is if we have the tangent with power of m x and then secant with power of n x dx. Actually, in your textbook, there are some explanation on how to determine the m and n, if m is odd, even. Okay. But I think it's not really practical way to see just from that. I think just take the examples, and if you can identify by yourself, I think it will be really helpful for most of the equations. So taking the tangent and secant. So let's give you example directly. So let's say we have the first example is tangent with power of 6 and secant with power of 4. Okay, remember, now because we are on the tangent and secant, we are going to have the identity secant squared x equal 1 plus tangent squared x. But how do we adjust this for solving our integral? Remember that when we differentiate the tangent, this will result in the secant squared. Okay. So if we take some substitutions, for example, we take substitution for the tangent, when we derive, it will be secant squared. So we may need to have separations from this tangent and secant. Okay, so we need to take maybe secant becomes secant squared, and the other part will be exchanged with this. So secant squared change with this, and perhaps we can take the substitution for the tangent, and we can cancel the secant squared. Yeah, I hope you get what my point is. So the point is, we are taking the tangent with power of 6 and secant squared and then secant squared. Okay. And then this part here, we get this 1 plus tangent squared. Okay. So we will have integrations. And now, before we multiply all these things and then maybe getting confused, from this part, if we remember that the tangent, we take the derivative, becomes secant squared. So if we let the tangent as u, we can cancel this, right? Okay, so all the integration becomes u with power of 6 multiplied with 1 plus u squared du. Okay, so we can take that. So let u as tangent x. So du will be secant squared x dx. So we can cancel the secant squared. So this will be u with power of 6 and then multiply with 1 plus u squared du. And this will be u power 6 plus u power 8 du. And integrate each of this, we get, and then I will exchange directly u with the tangent. So this is, we have, this is, we have 1 over 7 tangent with power of 7x plus 1 over 9. Tangent with power of 9x plus c. This is from the tangent with power of 6 and then secant with power of 4 dx.
Why not change all the secant to tangent?
You mean the secant with power of 4? Yeah, can you, but then can you solve it? Really? Let me try. Because as I remember, we will stuck at some point. Let me check this. We get this if we change all. The blue, the light blue here. This one. Yeah, can you solve that? Yeah, can you solve? Okay, so I hope you get the idea that
Why we are doing this thing here? Separate the secant squared, become 2. Because what we are doing here is our goal is taking this trigonometric identity and then rearrange the equations so that at the very end here we can substitute one of them and then cancel. So that's our goal in trigonometric integrations. As in the previous one, the sine and cosine. In tangent and secant, it's the same thing. Okay? The same thing. But there will be another perspective if we. So this is the power is even and even, right? So how about if the power is odd? Both are odd. The goal is still the same, but maybe we are going to have different subdivision.
okay. Okay. So let me erase this part. Okay, now the other one is the tangent with power of 5 and then secant with power of 7. So both of tangent and secant is having an odd power. Okay, how about this odd? Okay. Now the idea, since the basic identity telling that the secant squared well, you could always start from sine plus cosine squared. If you ever forget, this is tangent squared plus 1 equals secant squared, right? So since all
This identity, they are having an even power, and we have now an odd. So makes sense that maybe we are going to separate the tangent with 5. We move the tangent, so it has become tangent 4, and the secant with power 7. We move the secant, so secant 6. So secant 6 tangent 4, okay, and then secant tangent.
So let's try to adjust the equations. So this will be tangent 4 and then secant 6, and then this is secant x, tangent x. Okay, now we see that we have an interesting adjustment at the secant x tangent x.
If we remember that secant x tangent x is the result of the derivative of the secant, so perhaps that is the key. Okay, that's the key.
So if we can take this tangent with power of 4 and then substitute, if you remember that this is tangent squared is secant squared x minus 1. So if we take this secant squared x minus 1 and then squared, and then this is having secant with power of 6, and then we have secant x tangent x. When we have the u as a secant x, we are going to have a nicely canceling the secant x tangent x, right? Okay. Now we can have u squared minus 1 and then squared, and then u to the power of 6, and then cancel the secant x tangent x, and then du. Okay, then nicely done. Okay. And this will be 4. And then take integrations. U power of 10 is 1 over 11, and then secant with power of 11 x. This is 2 over 9 secant with power of 9, and then plus 1 over 7 secant with power of 7 x, and then plus constant. Okay, so the idea, whenever you see the arrangement, sine with power of something, with cosine with power of something, and tangent and secant with power of something, then we will see that perhaps this basic identity from the trigonometric will be helpful, and then you can solve the equations by substitution. So the key is to rearrange becoming this. So rearrange using the basic identity, maybe separating the secant, tangent. Okay, one more section, just a small part. Okay, aside from the case 1 and case 2, we also might have an integrations, sine 4x cosine 5x dx. How to solve this? And again, the key is to have the identity. Okay. So to solve this, is we are going to rewrite this sine 4x and cosine 5x as half. This is sine, this will be minus x, and plus sine 9x dx. I think you can solve this, right? So the product identity like sine, cosine, and then sine, cosine is also can be solved through the same way of this identity. Okay. Hopefully you still remember the identity. Okay, that will be the last part. Okay, the last, yeah, this is the last part. So the next sections will be still with the relate with the trigonometry. Okay, still relate with trigonometry. Okay, now, okay, we begin the next part. Maybe we will have just short introductions. We start with, let me give you example. See if you can maybe find out how to solve this. Okay. So we have an integral of a fraction that is 1 over x squared, and we have a square root of x squared minus 9. Not sure if you can you substitute.
be some way we could have, and take the square root and take the square. We'll have u squared on the right side. And then we have x squared is 9 plus u squared. But that will be, we need another method which we call the partial fractions. I think it still can. But what I'm going to tell you is, there's some interesting part on this x squared minus 9.
So if we review the trigonometric identity that we have in the previous sections, so we have first is sine squared plus cosine squared is equal to 1. Okay? And the second is tangent squared x plus 1 is secant squared x, right? Now if we look at how this can perform, so if maybe let me draw here. So if we take the sine squared, we can rewrite this as 1 minus cosine squared x. Okay, and in cosine squared, we can also write the same thing like that. And then for the tangent, we can write the tangent as secant squared x minus 1, or we can write yeah, I think just this one, right? Okay, so if we look at how it goes in this x squared minus 9, so we could see that this x is like our variable, right? Variable. And this is a constant. Okay. And if we compare with the tangent, we also have, this is a variable, but with a trigonometric secant, and this is our constant. And this has the same structure, that variable minus constant, okay? X squared minus 9. Okay. Now, how if we, okay, let the x squared becomes something that relates to the secant. Okay. So if we let this equal to 9 secant squared, and then we use another variable to substitute this, maybe using the theta to note the angle. Okay. So if we let this x squared become 9 secant squared theta, then we can write this with this, right? Okay. And then we can relate the secant squared x minus 1 with the tangent squared. Okay. So we can have the tangent squared x. So if we let the x squared as 9 secant squared theta, or x is 3, maybe we can start from x is equal to 3 secant theta. So we could write maybe let me move down from this part. Let's go around here and let me erase that. Oh, it's separated. Okay. And then since we are changing the variable from x to theta, we are going to take the dx of this 3 secant, and this will be 3 secant theta tangent theta d theta. Okay. So the equations, the questions, let me maybe rewrite here. So integrations, let me write the whole thing. This can be written as dx is changing to 3 secant theta tangent theta d theta and then the x squared is 9 secant squared theta, and square root of the x squared minus 9, as we mentioned before, is become 9 secant squared x minus 1, or this is going to be 9 tangent squared x, or this is not x, this is theta now. Okay. Now we can cancel. Maybe this one first. And then maybe this one becoming 3. So we will have tangent, and we can take out the 9 tangent squared. It's become 3 tangent theta. So we can cancel. So we have now, still have the integrations, don't forget that. The integrations, 1 over 9. 1 over secant is cosine. Okay. But we still need to integrate this, so we integrate. So 1 over 9 cosine integrate becomes sine theta. But this is not yet finished, because this is theta. The question is in x. Okay. So, okay. Don't forget that. Always drawing the triangle. And remember that our x is 3 secant theta, right? So secant theta is x over 3, or cosine theta is 3 over x. So if this is theta, so this is 3, this is x. This part here is x squared minus 9 with the square root. And the question is asking the sine theta, which is the square root of x squared minus 9 over x. And that is basically the answer that we want. So we are going to write the sine theta with this x. And then don't forget to plus a constant at the end. Now, what's the key behind all this process? It seems like really complicated, but the key is to determine this part here, a variable minus constant. So you could see that we could relate this to the secant squared minus 1. Because when we have that, we can relate a secant squared minus a constant, that if we can substitute the x nicely, we are going to have a tangent. So we have a tangent here, and this is the secant squared, and we can solve through this way. And eventually you will get the final result. So this is what we call the trigonometric substitution. So we are going to substitute, but not substituting like usually you would equal with some component, but we are substituting the trigonometry. So we let the x as a function of trigonometry. So x equal, for example, here is 3 secant theta. Okay, I think I will stop here for now, continuing next cases tomorrow, okay? And maybe having more exercise. Okay, and as usual, prepare the feedback questions. Just to make sure that we're confirming that we are taking the previous lesson. Okay, you finished yet? Yeah. Okay, let me start the feedback. Okay, let me start the feedback. I hope you finish your notes. Okay, start the feedback. I just want to know
our lesson on area and volume. The question has some calculations, but I'm pretty sure the calculation will not be very long. Should be very simple. But I think you need to prepare some notes to compute.
Okay, so I hope you guys get ready. Okay, so we'll start now. Okay, so if you miss out, you can go to the website and use the code, the number. Okay, let's start now. You can prepare your ID. I'm preparing 3 questions. Yeah, I think 6 to 7 minutes to in total. Okay, let's start. 3, 2, 1.
So you have a function f, function g, and you have the interval a to b, and you have the area and scan equation. Okay, should be false because we don't know which one is higher, f or g. Okay.
Okay. Let's go to the next one. Okay, so get ready. 3, 2, 1. Okay, you need to do some calculations.
4 minutes and 4 minutes and half. Yeah, around 5. The answer should be in a fraction, not in decimals. I'm not preparing decimals as a key answer. Well, you have 2 curves, the quadratic with a minus and the x squared, so it should be going up like that, right? And the bottom one is absolute value of x. First, you need to find the interval, the intersection. And then to help, you can imagine that this will be symmetry. You can imagine this will be symmetry. It is confirmed that this will be symmetry. Because absolute value is having just that v, like a v curve. And this is just a normal parabola. So to help your integrations and calculations, using the symmetry. So you just need to multiply by 2 at the end. small mistake. Okay, but you're already correct. But small mistake. It's 7 over.
Okay.
我刚才要按输入答案，那我就要请教，那我什么都没打。
Okay, one more question. I think, do we have time? I forgot I giving you how many minutes this one. 3 minutes. Okay, 3 minutes. Okay, should be okay. Should be okay. Okay, I think you can directly
Write, and you can decide which one is on the top, and then you can take the square, both curve, and subtract them. Subtract, take integrations. I think would be very fast. If you're not sure, you can take your calculator and if you just want to integrate, and make sure the calculator having the decimals, maybe the fractions, and using pi to give you the correct answer. I think you can adjust the settings for your calculator.
still have 1 minute.
1 is 44, 43. So 1 is. helpful is the final exam using calculator. Helpful? I think the important part is the process. Calculator is for confirmations and then maybe last computation when you have integration. Okay.
It should be E, okay? Okay, who is that? Okay, okay. Okay, then last part is the attendance and finish for today's class. Tomorrow we will continue the trigonometric substitutions and having some exercise on chapter 5, chapter 6. And please check the exercise, okay? And let me know which part of the question you need more discussion. Okay, finish, then we